So today we're going to continue talking about normal distributions. So in example 1, it says if test marks are assumed to be normally distributed and 70% of students scored greater than a mark of 60 out of 100 and 10% scored over 90, determine the mean and standard deviation of the test marks. So let's start by drawing out what we know. So we know they're normally distributed. And we know that 70% of students, so this right here, we'll make that be 70%, scored greater than 60. So scored greater than an x value of 60. They also tell us that 10% scored over 90. So once again, we can draw out a normal distribution. And we know that 10% scored greater than an x value of 90. Okay. Because this has to equal up to 100, if this part is 70%, then the other side there would be 30%. And if this tail is 10%, then we know the rest of it is 90%. And remember, we're using those two values because the z-score table actually gives us the percentage that is less than. So we're actually kind of working backwards here in that we already know what the percentage is. We're actually going to find the z-score. Okay, so we want to find the z-score that is closest to 0.3. Because that's 30% and 0.3000. Okay, so you're going to go and look at your table and you're going to try and find a z-score that is either equal to 0.30000 or the closest one. So here's my z-score table, and looking at all of these percentages on the inside, we are looking for the one that's closest to 0.3. So right here, we have that boundary of 0.3. So one of them is 0.3015, and the other one is 0.2981. So we want to ask ourselves, which is the closest? So this one's off by 0.0015, and this one would be off by a greater amount. So the one that's closest to 0.3 is right here. And if we read the z-score off that corresponds to that, it's negative 0.52. So that is the z-score for this first one. Z will equal negative 0.52. Okay. And we can actually fill in the z-score formula, right? Because we know z is also equal to x minus mu over sigma. We know the z. We know the x, because the x is 60. We don't know mu, because we are trying to find the mean, and we don't know standard deviation, because that's also what we're trying to find. And I'm going to cross multiply and multiply both sides by sigma to get an equation that doesn't have any fractions. And there I have one equation with two variables. And if we remember back to grade 10, if we're solving for two variables, we need two equations. So we're going to use this second set of data here about the 90% in order to get our second equation. So once again, we're going to find a z-score that is closest to 90%. Okay, so the one closest to 0.9, we have 0.8, 0.89. Okay, we're getting closer. Okay. And right here we have 0.8997, which is pretty close, and the next one is just a little bit over 90%. Okay, so this one's 90.15%, and this one be 89.97%. So the 89.97 is closer to 90%, so we're going to use that one. And the z-score that matches is 1.28. So just like before, okay, the z-score is 1.28. So we're going to fill in the z-score. We're going to fill in the x, which is 90. And then we have a mu and a theta. Or sorry, not theta, sigma. Okay, I'm going to cross multiply again to get 1.28. 6 equals 90 minus mu. So now we have two equations with two unknowns. And it's up to you how you solve this. You can do substitution or elimination. Both will work equally as well. I'm going to do elimination because both of them have mu's. So if I subtract these two equations from each other, I'll be able to cancel out that mu. So I've lined up my two equations here, and now I'm going to subtract them. So negative 0.52 sigma minus 1.28 sigma gets me negative 1.8 sigma. And then 60 minus 90 gets me negative 30. And my mu's, because they're the exact same, when I subtract them, they will cancel out. Okay, so now I can actually solve for sigma by dividing both sides by negative 1.8. And I get that my sigma is 16.67 to 2 decimal places. So there's my sigma. And then to solve for mu, I'm just going to sub sigma into equation 1. Okay, now I have my standard deviation. So I'm going to sub this into equation 1 or equation 2. It doesn't matter which one. So here I subbed 16.67 into my first equation. I worked that out. I moved the 60 over to the other side. So I got negative 68.6684 equals negative mu. I divided both sides by negative 1. And then I rounded my mean to 2 decimal places, so I got 68.67. Okay, and that gives us our mean and our standard deviation, which is what the question was asking for. So there's the first example. Example 2 here. It is found that a certain brand of light bulbs have a lifetime of 215 hours with a normal standard deviation of 12 hours. If the lifetime of the bulbs is assumed to be normally distributed, what percentage of the bulbs would you expect to fail in less than 200 hours? Okay, so they give us the average lifetime of 215. That would be our mean. And they give us our standard deviation. So they give us our sigma. Okay, and we want them to fail in less than 200 hours. So we are really trying to find the probability of x being less than 200. So we're going to draw this out. It's a normal distribution. Our mu is 215. The x is going to be less than that, so we will expect a negative z-score. X is 200. And we're trying to find this area right here. Okay, so we're going to start with our z-score. Our z-score is x minus mu all over sigma, which is negative 1.25. So then take a minute, go to your z-score table, look up negative 1.25, and then come back and replay the video. So if you look it up in your z-score table, you should have gotten that the probability is 0.1056, which is really 10.56%. In part B here, they want them to have a lifetime of more than 250 hours. So the probability that x is greater than 250, remember that's really just 1 minus the probability of x being less than 250. So we're going to draw out our normal distribution. Our mu is always the same, it's 215 for this question. And we are trying to find when x is 250. And we want it to be more than, so our goal in the end is going to be to find that blue area. So we start with our z-score. So we're going to do 250 minus the mean divided by the standard deviation. And we get a z-score of 2.92. Okay, and then if you go and look that up in your table, that would be 0.9982. And when we do 1 minus that, we get a probability of 0.0017, okay, or 0.17%. And that is our light bulb question. So in our next question here, it says, in a certain process, ball bearings manufactured on Earth have a mean diameter of 2 millimeters and a standard deviation of 0.01 millimeters. Using the same process but manufacturing them in space, in general, in the absence of a gravitational field, the bearings have a mean diameter of 2 millimeters and a standard deviation of 0.001 millimeters. Bearings are rejected if they are less than 1.98 millimeters or greater than 2.02 millimeters in diameter. Assuming the diameters are normally distributed, what are the rejection percentages under each environment? So I want you guys to pause the video and give this question a try, and then when you replay it, I'm going to pull up the answer. So I've drawn two normal distributions, one for Earth and one for space. Okay, so both of them go between 1.98 and 2.02, but the difference between them is really just the standard deviation. Okay. So because we're trying to find between two values, we need to find the z-score for each of those two values, and then the probabilities that match. And so to find the probability of it being within the acceptable range, we take the probability of x being less than 2.02 and we subtract it from the probability of x being less than 1.98, and that gets us the acceptable percentage. Once you know the acceptable percentage, you can find the rejection percentage by doing 1 minus the acceptable percent. Okay, so on Earth, you hopefully got that 4.56% will be rejected. And then you're going to do the exact same thing for space. So you're really doing the same process, just the z-scores are going to be different, so they're going to, the standard deviation will be different, so it'll give you a slightly different z-score. And when you did that, you should have gotten that the non-rejected area was 1. And that means the rejected area would have been 1 minus 1, so 0% rejection. Okay. And the rest of the lesson will be continued in a second video.